This is lecture number 15. Do you have any questions from previous class? Okay, so right now we will continue with the noise analysis or noise sources in charge pump PLL. And yesterday at the end of the class, we looked at uh, two sources. One was charge pump and the other one was resistor in the loop filter. Okay, the next most important I'm talking about it in the end, but this is one of the most important one is oscillator. Okay, as a noise source. So we will go in detail how the noise actually means what are the noise sources within the oscillator and what is the reason behind a certain noise profile of an oscillator. That will depend on different oscillators which we will look into. But right now the only thing which I want to talk here is that the noise in an oscillator is, if we look at a phase noise of an oscillator oscillating at a given frequency f0, the oscillator phase noise is something like this, which is actually minus 30 dB per decade. So this is with respect to frequency. This is phase noise or power spectral density of phi VCO. Okay, and beyond a certain frequency, this is normally called as a flicker noise corner. Let me just call this as FC, which is a corner frequency in oscillator phase noise, and this is minus 20 dB per decade. Okay, and this is the noise profile, noise spectral density of an oscillator, which is in an open loop. So it is not in a closed loop format. So why the profile looks like that, we will look into detail when we go into the oscillator design itself. But let's say if you are given this noise profile of an oscillator, and now you are asked to find the total output noise. So right now the description is limited to that part. Now, for an example, means we know there are different kinds of oscillator. One is ring. Again, this one I will go into detail in, I think, after a few lectures. So ring oscillator, which is means the simplest one you can say is an inverter ring connected in feedback, and this is the output. The control is the supply of, so this one is ground and this is V control. Okay, and the output is V out. So now this is a ring oscillator, means it's based on the inverter. This is called as a ring oscillator because the inverters are connected in a ring, and I want to find the phase noise of this particular oscillator. This is one thing. This is one kind of oscillator. Other kind of oscillators are LC oscillators, which are, these are very two broad categories, which are LC oscillator is based on the resonance frequency of an inductor and a capacitor. Okay, and because any real LC comes with a unwanted impedance, which is, let's say, R. So in order to have a sustained oscillation, you try to create a negative. Again, please do not worry about what am I in detail of this. We will go into much detail of these kinds of oscillator. But this is another kind of oscillator where the oscillation frequency is, if I say oscillation frequency here is dependent on your LC, and in this case, in the ring case, the oscillation frequency is omega is equals to 2 pi by the delay of each inverter. So this actually, if Td is the delay of each inverter, then the oscillation frequency is this. Td delay of each inverter. I just showed you here that, okay, these are the two broad kind of oscillators which we will discuss later. But let's say you have this oscillator and it oscillates at a given frequency and you want to find the phase noise of this oscillator. Okay. So the phase noise of this oscillator, as we talked yesterday, it is like with respect to the carrier always. So how do we find the phase noise of this oscillator? I will show you some like simulation part of this. So for an oscillator oscillating at a given frequency fc, which so it is periodic with this carrier frequency, right? So you need to do a periodic steady state analysis. Let me see if I can write it here. I can't. So for phase noise simulation of oscillator, phase noise simulation of oscillator means this is for any of the oscillator, whether it's a ring or LC or any other kind of oscillator, right? The first one is you need to do a PSS analysis in your spectra, whichever simulator are you using. This is periodic steady state analysis. Okay. You can look into detail of PSS in any of the help manuals. So it will find the operating point with respect to whatever the periodicity it is having. Okay. So this one, and then you need to do a P noise, so this PSS analysis has to use the carrier frequency of the or F naught, which I can say the output frequency of oscillator. Okay. And how do you know what is the output frequency of the oscillator? You make a ring oscillator or any oscillator and you run in transient simulation. You find out what is a period or an average period. Okay, this is without noise. So you run the transient simulation on an oscillator without, in the absence of any noise, and you find what is an oscillation period. And you can give that oscillation period as an initial value or the initial frequency to your PSS analysis. So actually, the PSS analysis asks you this beat frequency. This beat frequency is a period of the oscillator, like frequency of the oscillator. If you do not know the beat frequency, if you give any arbitrary frequency, then the PSS analysis may not converge at all. Maybe it is much far away from the actual oscillation frequency. Okay, and you have to specify the number of, so this part is beat frequency, then you have to specify the number of harmonics, that how many harmonics are you considering. These harmonics needs to be used for your noise conversion and other reasons. So in this case, then you have, you can save the time domain results also in this case, like 100 nanoseconds, I have just put the number here, that before finding this, before finding an operating point, you need to run a transient simulation also, which is done by the PSS itself, and it finds whether this is periodic with a given period or not. Okay, so let's say here you give a 1.6 gigahertz frequency, and when it does the PSS analysis, it finds an actual period, which might be 1.603 or somewhat nearby. Okay, so you save these transient results. If you want to see the transient period after doing the PSS analysis, you can do that. And let's say if you give this the time for stabilization. So this is also important. So this is like, let's say your oscillator takes a time of 1 micro. I'm just like amplifying it. If your oscillator takes a time of 1 microsecond and you give the time for the PSS analysis like 100 nanosecond, then your oscillations will not build up. It is not a stable oscillation at all. So how much time are you going to give for this thing for stabilization? You should get it prior by doing a transient simulation independently. Okay. Then the oscillator nodes are output, the nodes are specified, and if you are not having any noise in the system, it may turn up that the oscillator doesn't build up at all. Means it just sits at one point, and that is very much possible when you are using, we will see some kind of differential oscillators. Okay, so you can give initial convergence values also for the simulation to start. So once you have the periodic steady state PSS output, then you do a p-noise analysis. Okay, and this p-noise, let me just write it the other way. Periodic noise analysis, and this will find the, so in Spectre you will see that, yes, for the p-noise analysis you need to give the beat frequency which you have got from the PSS. So same frequency, beat frequency is specified. Now I want to find the noise relative to the carrier. So here you see that this is something as a sweep type. Okay, this sweep type is relative, it's not absolute, and this is relative to the carrier. Okay, and the first, and I am looking only for the first harmonic, not the second harmonic. So that is the number here. Then start and stop frequencies, that depends on what you want. In this case 10K to 100 meg. And how many sidebands you want, this will be used for how much noise is getting converted at your so in an oscillator, the noise at the whatever the oscillation frequency is, the noise will also be converted from the harmonics of the oscillator output frequency. So that part, yeah, around FC. So when I specify here 10K to 100 meg, that is like this output frequency for the noise analysis, it will sweep from FC plus 10K to FC plus 100 meg. Okay, and FC minus 10K to FC minus 100 meg. So it is around that frequency. Yeah. So no, then it will do only at 2 FC. Okay. So means if you are having any oscillator, you will see that I will have, means if the output is close to a square wave, you will have a dominant second harmonic, which you can observe. So the second harmonic will also have a noise around it. So this one is for F. So let's say this is your FC, right? Then there will be some component for 2FC also. So if so the noise, if you do a relative harmonic one, the noise which you are going to find is this. Whereas if you do a second harmonic, relative to second harmonic, the noise which you are going to find is this. Whereas if you do an absolute, the noise which you are going to find is with respect to DC. You do not know what that noise is, means here. Okay. So when you are doing a PSS analysis for all these oscillator purpose, you look at you find the relative frequency. Okay. Whereas for if you want to look the noise at DC, then you will do an absolute, which is actually done in other system like switch caps. If you are, let's say you are having a switch capture filter, right? So when you are having a switch capture filter, you look the noise from the DC. I think, have you done any other switch capture circuit or no? So I'll just give you, this is for the PSS, this is nothing related to PLL. So let's say I am having a MOS switch, okay, and I'm having a capacitor, and there is a certain clock phi which is sampling it. Okay, so you know, so the phi is something like this, and this is like V in and V out. Okay, so you know if switch is always on, it is acting as a resistor. Okay, So if it is a resistor, then V into V out is a low pass transfer function if it's always on. But because you are sampling it, right? So this filter means you will still see it as a filter, right? But then so the response of this filter will be, you will have some filter response at DC plus whatever your sampling frequency is, FS, 2FS and all. Okay. Now, if I am looking from V in to V out as a low pass transfer function, I want to see what is the noise contribution of the switch resistance itself from 0 to this, whatever bandwidth I am looking at. Let's say this is the bandwidth I am looking at, or with respect to DC. In that case, when you are doing P-noise analysis, you should do an absolute one rather than a relative one. So whether you're doing absolute and relative, that depends on what sample system are you using or what are the other requirements. Okay. So once you do the P-noise analysis and the output of the noise, here you can choose. So here if you look, there are a couple of things. Here there is no input noise source. This is an oscillator. This is not a, you have an input and output gain, anything involved. So input noise source is none. And sources, this is a single sideband noise analysis. Single sideband noise analysis means that the values which it is going to give is only this part of the phase noise. It is not going to give the combine of the, like the edit two. Okay, and in most of the cases, it is symmetric across around the carrier. So if you are going to use this noise in your analysis, you should think that the actual noise is twice of this. Actual phase noise is twice of this. So you add 3 dB to the final numbers, whatever numbers you get from here. Okay. Pardon? Phase noise, it's not that phase noise is single sideband. We always treat single sideband for our analysis. Okay. Phase noise exists around the carrier on both the sides. So for any any system which you are using will be a narrow band across the carrier, right? So the noise you should consider plus and minus delta across around the carrier. In all these cases, because you are having a symmetry around the carrier, that's why you only treat a single sideband noise. But for the total noise analysis which you are going to do, you add a 3 dB to this number. Right. So you do the phase noise analysis and then you can plot the phase noise. You will go to tools, results, and there you will have PSS and P noise. If you actually save the transient results, then you will find another tab here which will say that you have the transient T stable thing. You can plot those, and you can plot the phase noise from here. Okay, and this phase noise plot will look something like this. So you can have an oscillator which gives you a certain phase noise. Now this phase noise you can use as in your analysis which you are going to do to find how much jitter it will be. Means without closing the loop in circuit, you can find what is the actual noise of an oscillator. You can use that number in your like in your analytical, or just a simulation on equations. No closed loop simulation in schematic yet. Okay, and the other easy part will be that let's say once you find the phase noise and you know the relation that if I double the power, my phase noise will reduce by 3 dB. Okay, so those things you will find when you actually design an oscillator. So if I find, let's say for 1 milliwatt, I get a minus 90 dBc at 1 megahertz of whatever noise profile I got, right? Then I want to, and I do not get enough jitter. Okay, then the thing is, oh, I have to like increase the power to reduce the noise. So even without coming back to the again this spectre simulation, I can just say, okay, I will reduce the phase noise by 3 dB, which is actually going to cost me a twice the power. So I can do that simulation in MATLAB or whatever without coming back to the circuit again. And that thing you can easily, I do not know how easy it will be. Let's say I have this ring oscillator, okay, and I'm just telling you how the scalability of the power and noise will get affected. Okay, so this has V out, and I get a phase noise of, let's say, minus 90 dB, whatever phase noise profile. I'm just saying I get 90 dBc per hertz at 1 megahertz offset. Okay, this is what I designed, but I find that this is not meeting my final jitter requirements. So I need to double the power, or I need to reduce the phase noise. So the easier way is, if I double the power, my phase noise goes by 3 dB. This we will get it when we do the actual ring oscillator phase noise analysis. Okay. So in simulation, I made it 93 dBc per hertz, and I again do my final jitter calculation, and I know this is going to cost me 2 milliwatt of power. Okay, and then I come and I find that if this number is working for me well, then I come back to the schematic and I want to increase the power, and I do not want to change any output frequency or anything. I want just phase noise scale very nicely. So if in one case my phase noise was this, I just want it to reduce by 3 dB everywhere. I want this transition. So what kind of scaling can you think about? Without changing the noise profile, it's just scaling by 3 dB down. What can I do to the new circuit or in the schematic? Huh? What do I do? No, increase the whole thing is how to increase the conductance without change. So this is more on the real implementation side. Okay, means if I increase conductance, I am surely going to get a power, but I do not want to get any change in the output frequency or noise. Means I want to maintain that scalability as linear as possible in this sense. Connect two in parallel. That is the easiest way. You can double the power and you can get the same frequency. So it's like I just copy that oscillator and connect node to node. This is actually connecting two in parallel. If you do that, you can maintain the scalability. Means other than the layout parasitics things change, but other than that, the scalability will be there for sure. Okay. Any questions? So with this, we actually conclude the noise analysis of a charge pump PLL, where we didn't go in detail actually for the oscillator itself, how the oscillator noise and other things come up. We will take that up when we look at the building blocks of the PLL. So now you can at least do this basic analysis of what jitter you want from for what parameters you need to have, what jitter you will get from a PLL. Okay. So the next session here for the noise analysis. Now we start with the building blocks of PLL. Now we will go actually in the schematic of circuit design. Building blocks of charge pump PLL. So just that no one has forgotten the basic block diagram. So I have PFD, then charge pump here, and loop filter, which we type 2 plus is control voltage goes to VCO. Then I have a divider, and so this one is phi in, this is phi out. So I hope everyone recalls that. This is like we went into the noise analysis and everything at this block. Okay. So this one is type 2 order 3 PLL. Okay. So the first building block which we look at is phase frequency detector. Okay, and the PFD, which can be used for phase error and frequency error detection, we have seen that is a three-state phase frequency detector, and we very nicely drew it other time with D flip-flops. This is connected to VDD. We have Q, Q bar, and then other block is this V, again D and Q, Q bar, and that is reset using a AND gate. Okay, so this is the reset, and this one is up and down. Okay, so now in this was the block diagram of the PFD which we have seen, and the signals or the time domain signal diagram for this flip-flop. Let me just show it once more. I have R and V. Okay, now this is R and V. So let's start considering all the logic delays which exist in the system now. Okay, so as R goes high, your up will go high with actually the delay of the flip-flop, whatever the delay. So let me just have some more. Let me just make it slightly wide so that it gets easy a little bit to understand. Okay. As R to V goes high, my up goes high with some delay, which is the delay of the flip-flop, and it remains the same till the time V goes high. And when V goes high, then you can say the down signal will go high after the clock to Q delay of the flip-flop, or signal to output delay of the flip-flop here, and this is the same. This delay and this delay are the same, right? So this one and this goes high. Now the thing is, when up and down both goes high, then there is a one end clock delay, right? And after this end clock delay, then it will be reset to output delay. Then only down will go to 0. So down goes 0 here, let's say. When down goes 0, the up will also go 0. Okay. Now this is actually your P and this is AND 2, means two signals it is ANDing, plus your T of reset to Q delay. So this overlap reason exists. Okay. Now what happens to the reset signal? In this case, reset signal, so when down signal goes high, then after an AND delay, so from here there will be a delay which is actually your AND delay, AND gate delay. That time the reset signal will go high, and then it will remain high for the T reset to Q delay, and it again become to 0 after an AND delay. Okay, so this one is also equals to T and 2 plus T reset to Q. Okay, the only thing is that this is T of N2 delay. Okay, this is the logic delay which is involved. So what you see that even without explicitly adding any overlap time, I am still having an overlap time for my between up and down. The only question is whether this overlap time is enough for my switches to switch on. Okay, so if I want to have a T on which is greater than, in this case, whatever you have seen, T of N2 plus T reset to Q, if that is the requirement, then I will go and add another delay in this path. Now, with that added delay, I will get T on equals to Tn2 or T reset to Q plus tau delay, if that is what I am adding. T on is the same as T overlap. Okay, so I can get the overlap time. But what happens as a consequence of this is that your reset clock is also high for the same time, which is the same here in this case, as I have just shown you here. Okay, so if you want to increase the on time overlap time, you will actually are increasing the reset time also. Is that any problem? So let me show you where it can cause a problem and then it becomes better. So let's say when you have an R and V signal like this, which are very close, our phase error is smaller. Okay, this is delta T, this is R and V. So the final reset signal which you are getting, now I'm drawing just ignoring some delays, but just giving the finite reset time, will be this. Okay, now the same thing, look at the, in case my V signal moves to very close to, sorry, this is not, my V signal actually rises here. Okay, so that means I am moving slightly, means I am moving closer to 2 pi. Okay, if I move closer to 2 pi, then this signal, the reset signal, can actually occur somewhere here. Let me, so here. Okay, if my reset signal occurs at this node, this is the reset, and we know during the reset time, means after this T reset to Q delay and other, your up and down signals are actually forced to 0 when reset is high, right? Now if reset is high and I get another transition here, what will happen? It won't take it. So this transition is missed. Now as a consequence of missing this transition, now look what happens in the next cycle. So I have the same clock, and okay, so in first case you were having a up minus, so let me just plot with the black. When the phase error were very small, your up minus down signal was this. Okay, whereas when the phase error increased, your up minus down signal actually increased like this, right? So you are still positive, you are still maintaining a positive error, but now you missed one, you missed one transition. Now your your V signal is coming before up. So what you will see is that you actually get up minus down signal here. Okay. So because of a finite reset time, when you are close to the phase error of 2 pi, you actually miss the transition in this kind of phase frequency detector. And when you miss the transition in the, and this will then continue in all the consecutive next cycles, that your phase error actually becomes negative. So now if I go and plot the characteristics of phase frequency detector, so initially it used to be this 2 pi, this is phase error, and the y-axis is v of up minus down average, and this is on the negative side is symmetric in the other direction. Okay. Now what I see, if you go to a certain point, let's say this point, after this, depending, this is again a function of t reset. After this, you will have a negative phase error. So then what happens is you actually have this. That is the new characteristics of the PFD. Okay. And this time is dependent on T reset. Okay, this you can calculate with ideal clocks, that if it goes just cross that, then you will have a up will not, means it will miss the transition. So this phi range is actually, let me just call it as rather than delta phi. This delta phi is equals to 2 pi times T reset by T reference. So let me just write TR is reference period. Okay. If you remember when we started initially, the XOR PD or S flip-flop phase detector, we told that even for the positive phase error, they are having a positive and negative also, negative regions also, which is the one reason because their frequency acquisition range was very limited. Right now with the PFD, we are landing up in the same problem because of the way we are implementing it. Right. So if I ask you, means if you remember EXOR or SR flip-flop based phase detector, the average on the positive phase side was 0. You have a positive and negative, whichever one you looked at, right? Now, if with this kind of phase error detector, I'll end up in the same region, means I'll end up having an average 0 for the positive phase error, what should be T reset? So first thing is, let me just first point, because of this positive, like a finite positive and a negative response for a positive phase error, you will actually limit the frequency acquisition, frequency range for acquisition. Okay. Now, the question I am asking is, what should be the T reset, or what is the maximum T reset which you can tolerate before your frequency acquisition range actually gets severely limited, where average goes to 0? Pardon? Half the T ref. So in terms of, so I'm just writing that as a equation, that the delta phi should be less than pi, right? That's the equation I will use, so that you have 2 pi T reset by TR less than pi. So 1 by TR is less than 1 by 2 T reset. Okay. This is nothing but your reference frequency FF. So the operator operating frequency of PFD is getting limited by the reset time which you're having in this particular PFD. So think about the same thing that if you want to run the PFD at 1 gigahertz of frequency, which is one clocking at 1 gigahertz, and you want to have a reset time equal to a nanoseconds or half a nanosecond. So in this case, if my FR is equals to 1 gigahertz, then your T reset should be less than 500 picosecond. It cannot be more than that. And in that case also the frequency acquisition range is very, very limited. Okay. So this is the problem with this PFD implementation, and this is also the reason why you want to, let me just write it, limits operating frequency of PFD. Okay, and this is also the reason why you do not want to have a larger T reset time. So you want to have a smaller T reset time as possible. Okay, any questions? Actually, in all the current like lower technology nodes, your T reset time will not be more than 100 to 200 picoseconds. Because your switches for you, which you are using for a charge pump, they actually act very fast. Okay, so but again depends what kind of current you are pumping and the other things. And this is like with respect to the reference period, and reference periods are not more than gigahertz. A reference period is too high. You're mostly limited within max of 100 or few hundred megahertz. Okay. Okay. So let's look at this is if you use a D flip flop and do that, this is surely is going to work. But then there exists different kinds of implementation for this PFD, which are more simpler or use less logic gates. Okay. So the first one is, so we will look for a couple of them. One is NAND gate based phase frequency detector. Okay, so let me try to insert a picture if I can. Let's see, I tried it, but so it's not moving actually. Okay, so let me just go with here only. So I'm just taking part. No. Okay, so let me just stick to this and see. So this one is a NAND gate based PFD. It is all made of NAND gates. And there are a few things that I will highlight here. This is actually the reset signal here is actually a active low reset. So you can say it's a reset bar. Okay. And this is actually it is active to the falling edge of R and V. So now let me show you how this works. So let's mark some point. Let's say this is our X node and this one is our Y. Okay. And so, okay. So let's say when R was high, so I will remove this part here. When R was high and V was also high, in this case. So let's say the R and V signals are like this. Okay, and the reset signal was actually, this was also high. So this is just to show you that uh, when R was an up bar signal is, so let me say, okay, up bar signal is also high. Please, I'm just trying to show that, okay, this is something, the circuit works here, okay. If you make it, you should not get confused with it. So when R and up bar are high, you can say Rx is low, right, as per the NAND logic. So Rx is low, and when Rx is low, you can see that this Rx is also going to the NAND gate, which is having a 4 inputs, right? If the input to one of the input to the NAND gate is low, then you are having actually the output reset bar is high. So the logic satisfied here, and this will hold for the same V also. Now, as R goes low, your Rx is going to be high, right? Rx goes high, and what will happen as your Rx goes, so your actually Ry was actually high before. So now your reset bar was high, your Rs goes high, Ry was already high, so your actually up bar goes low. Okay, you see that transition, right? And so this will remain as such. Now when V goes high, sorry, V goes low, because this is all a falling edge active. When V goes low and down bar actually goes slow here. Okay, so down bar goes low, then what happens? So when down bar goes slow, let me just keep, I'm marking the other points as Vx, this node, and Vys, this node. Okay, so when down bar goes low, at that time your Vx node goes actually high, as like Rx node. And when Vx node goes high here, okay, this is red only. So now you see Vx node, Rx, Ry, Vx, Vy all are high. Once your V node goes high, then the output of the NAND gate will actually go low. Right. So your reset after some time here it goes low. Okay. And as soon as the reset goes low, your down bar and up bar again becomes high. It's after some delay. Your up bar and your down bar, so they will become high. Okay. So and then your reset signal will also become high again. So this is an active low reset which I was telling. It resets when it is low. Okay, and this is with respect to the falling edge of the clocks. Okay. Now, in this case, what is the T overlap time? Those are the things which we need to see. Okay. So T overlap time is T NAND 4 plus T plus whatever TD is here. Because once V goes high, it's only the reset signal means it's the delay from the NAND 4 gate plus TD that it changes, right? Whereas T reset signal, now here T reset signal is actually the time for which the reset signal remains low. Okay, time for reset signal to be low. Okay. Now this T reset signal is, if you look at, once reset signal goes low, it actually goes through this NAND gate, then this NAND gate, and then come back to the NAND 4 and the delay. Okay, you got that idea? Is there anything confusing here? Once your reset signal actually goes low, that has to propagate and make your Vx and Vy change. Actually, Vy change, right? And then again, NAND delay will be there. So your reset signal delay is T NAND 4 plus 2T, NAND 2 plus your tau d. Okay. So in the D flip-flop case, we saw the T reset was T equal overlap, but it very much depends on the implementation. And in this case, your T overlap is greater than T reset. And we know that for the time for which the T reset is active, at that time your up and down cannot change, means you cannot entertain any signal. So you will have the missing edges. Okay. So what we want means, ideally we want T overlap, means, let me say, ideally T overlap equals to T on, which is the on time for the switches, on time for charge pump switches, and we may like to increase T overlap depending on technology requirements. Okay, but we want T reset ideally to be 0 so that we do not miss any edges. Right? But in this particular case, you see, if I increase T NAND 4, I increase both proportionally. There is no change. Okay, so within the same circuit, actually there is another version for this circuit which has increased. So now, if we are if we are changing any of this T NAND 4 and tau d, we are actually changing T reset and T overlap. But there is another circuit which is in the same, which is this one, which actually you see now the up bar is no more this. I am taking up bar after a delayed version. So in this case, you do not change any of your T reset. The only thing happens is your T overlap actually increased, and T overlap increased by 2T NAND 2. I think you can see that whether it's a 2T NAND 2 or 1, you can check that part. Okay, because now, so think about it. When let me write it with a different pen. This was the previous up bar, right? Now when the previous up bar changed, in response to that, your first this NAND logic is going to change, right? Means previous up bar, your this NAND output Rx will change, and then your Ry will change, right? So actually you add another added 2 NAND gate delay to overlap time. Okay, so here we did not decrease the T reset, but we increased T overlap if required. Okay, so but in both these cases, you will still see that the NAND, where was I? Means you will still see this limiting factor on the operating frequency of PFD and the frequency acquisition range thereby. Okay, so let's stop here and we will look the other blocks later.